score. So if it was a test, I'd expect 95 out of 100 kids to get a mark between 40%, which is 2 standard deviations to the left, and 70%, which is 2 standard deviations to the right. In terms of area then, what is this area that I've done in yellow here? Anyone? What's that area then in yellow? Well, the probability of that area is 95% of the area under the curve, right? Because we said there's a 95% chance here of the area falling within 2 standard deviations of the mean. So this area is, in yellow, is 95%. So in other words, this area in yellow here is 0.95. Okay, so in other words, there's a 95% chance, okay, or a probability of 0.595% that between 40% and the kids got between 40 and 70%. Kind of with me?
So isn't it 30 and 70%?
Yes, it is.
I could be wrong.
Well done, Raisa. Thank you, Raisa. High five yourself. Okay, so I'd expect 95% of students to get between 30% and 70%. Okay, and then what would this half area then be? What would that, from the mean, from there, okay, to there, to the right of the mean in the yellow region, then that area would be 0.475. How did you get that? 0.95 divided by 2. Okay, in other words, there's a 47.5% chance, okay, that somebody got a mark between 50% and 70%. Or else you can look at it as 47.5% of the class would get a mark between 50 and 70%. Capish?
Kaposh.
Okay, well done here with Kaposh there. Okay, and then the last one, 3 standard deviation interval, just about everything. Okay, if something is normally distributed, just about everything will fall within 3 standard deviations of the mean. So, let me grab another pen. I would expect, okay, in that region over here, so in other words, in the green area, I'd expect almost 100%. I think it's, what's it, 99.7%. If something is normally distributed, I'd expect 99.7% of people to get a mark 3 standard deviations to the left. So we started at 50, 40, 30, 20, and 3 standard deviations to the right, which is 80. Okay, so I'd expect nearly 100% of people to get a mark between 20% and 80%, on condition, that's over there, sorry, that it is normally distributed. Okay, so tell me please, Daniela, what's the probability of a student in this class getting between 50 and 80%? Well, what's this whole area over here, Daniela? It says 99.7%, right? So between 50 and 80 will be?
50 and 80, that divided by 2.
Yeah, so it'll be 99.7 divided by 2, whatever that is. Okay, so about 49%. Yeah. Okay, so the symmetry in a normal distribution is really important. And the other really important thing is what kind of data we're working with? Continuous data. And why that's going to be important, okay, is this idea, guys. If I said to you, if data is continuous, so let's say somebody's running a race, okay, and so here is a continuous distribution for the times. I don't know. So the mean is, let's say, 20 seconds, right? Okay. And I said to you, what's the probability of somebody getting exactly 21,053,217 seconds? Okay. We say that an individual probability in continuous data is 0. Okay. Because that data can theoretically go on forever, the probability of somebody getting that exact time we consider to be 0. Okay, and that's why there's a bit I'll go through now where it doesn't matter if I say what's the probability that a score, probability that X lies between 10 and 20. It doesn't matter if I put an equal sign or not, because the probability of getting exactly 10 is 0, and the probability of getting exactly 20 is 0. It matters with discrete data, but it doesn't matter with continuous data because of this idea that the probability of something individually happening is 0. Raisa, does that make any sense?
Yes, sir.
Okay, because with continuous, it's so unlikely to get that exact time, okay, that it's 0. All right, I don't know if I'm making any sense, okay, but we're doing our best, guys. We're doing our best. Right, just a couple of other things that I wanted to mention. in the textbook before I try an example. Where were we? Okay, so this is just an introduction. I don't want you to worry about that. Can you guys see the pages? I don't want you to worry about this experiment really. The only thing I want you to worry about with this is this idea over here. Okay, what's going on over there? Properties of normal distribution we've just discussed on page 160. Over here, just make a little note. Okay, so like the idea of nothing, probability, area is probability under the curve. And here, guys, is an explanation for this. Because the probability at one specific point is 0, and this only works for continuous data, okay, then whether you put an equal sign or a non-equal sign doesn't really matter, okay? Just one thing which I find fascinating, okay, is that this, okay, the formula, okay, for the probability of something, okay, between A and B, okay, is this integral formula. Where did they write it here? Okay, it's the integral between A and B of this is the formula for your whole curve for a normal distribution. And you don't have to worry about this. You're never going to have to use this, but that's where you're going to get our table from. But what I find quite fascinating, which maybe you won't care about, is that within this, okay, you've got two irrational numbers, pi and e, okay, which I think is quite remarkable. Okay, that in stats we have that flight, that the area, the ratio of the area of a circle over the circumference over the diameter pitches up in a normal distribution. Anyway, okay, so I want to go and jump, okay, to this idea over here. Okay, so the problem is this. Okay, there's that complicated formula. If you go to page 164 of your notes, okay, theoretically speaking, if you're going to work out, you'd have to use this formula back here every single time you wanted to calculate an area under a curve. Why do I want to calculate an area under a curve? Because that's your probability of something happening in a region for continuous data. Theoretically, you should have to go do that every single time. But there's good news, okay? And the good news is that what we're going to do is we're going to take every single normal curve, okay, no matter what the mean is and no matter what the standard deviation is. So we could have an example like we just did, okay, where the mean was equal to, and the symbol for mean is mu, eh? So let's say the mean was 60 and the standard deviation was 10. Okay, and that gives us, it will give us a normal shape. But what we're going to do is we're going to convert, okay, every single normal distribution with its mean and its standard deviation into what we call the standard normal distribution. Okay, and the reason why is because we can draw up a table, use a table for a standard normal distribution. Okay, so in a standard normal distribution, we say that the mean is equal to 0 and the variance is 1. And if the variance is 1, then the standard deviation is 1. So in this, okay, is your standard normal distribution, okay, which you're going to work from the table from. And all that's saying is that if you had your mean is 0 and your standard deviation of 1. So you'd expect 68% of your data to lie here. In that region, we'd expect 95% of your data. In this region, 99.7% of your data. And what we're going to have to do is we're going to have to take every single individual X score and then use the mean and the variance and the standard deviation to get a Z score. Okay, so your process is always going to be this. Okay, get a Z score, okay, using that formula, and then you're going to go to your table to read off the area. Okay, you're not going to quite get everything at this point. Let's just try. So what they're saying here in this diagram, okay, which is really important, we took this example here, had a mean of 60, okay, and a standard deviation of 12. So this is one standard deviation, that's two standard deviations, one standard deviation to the left, two standard deviations to the right, okay? And so instead of working with that, we're going to, these are your X scores. So the actual mean is 60, okay, then one standard deviation away, it's between 48 and 72, okay? And we convert your X scores into Z scores, okay? And all Z scores are is how far an individual X score is away, how many standard deviations it is away from the mean. So what we're saying here is that if I convert, okay, at the mean, at x is equal to 60. I'm going to be using this formula over and over again. At x is equal to 60, okay, I'm going to use z is equal to x. So your x is 60. Okay, this is your x. Your mean is 60, and your standard deviation is 12. So if you work that out, at x is equal to 60, we say the z-score that goes with x is equal to 60 is 0. Okay, why? What does it mean? It means it's nothing, it's not away, it's at the mean. Okay, it's nothing away from the mean. However, at x is equal to 72, okay, if I look over here, at x is 72, okay, how far is 72? What a z-score is how far is that away? How many standard deviations is 72 away from the mean? Well, it's the difference between the x-score and the mean. That's how far. It's 12 away from the mean. And how big is one standard deviation? One standard deviation is 12. So x-score of 72 is how far away from the mean? Well, it's one standard deviation away from the mean, right? So if x, for this particular sample, if x is 72, your z-score is 1. Daniela, are you getting any of this?
It's making
Daniela.
sense.
Does it make some kind of sense?
Yes, it does.
Okay. So at x is equal to 84, okay, because the standard deviation for this data set is 12, okay, how many standard deviations is 84 away from the mean? Well, you could do it intuitively here. You could say it's 2 standard deviations away from the mean. So for this sample, x-score of 84, okay, will have a z-score of 2 because it's 2 standard deviations away from the mean. And if you use the formula though, okay, at x is 84, that's if you use that formula that you're given, and this is given to you by the way on your information sheet, you'd have what the x-score is 84, the mean is 60, okay, so it's 24 away from the mean, okay, but the standard deviation is 12, so 24 divided by 12 means that it's 2 standard deviations away from the mean. Likewise, at x is equal to 96, okay, you're going to get your data. This is 3 standard, 12, 12, 12. This is 3 standard deviations away from the mean, and it's to the right, so it's positive, right? So here, you're going to have 3 standard deviations. Okay, that's why an x-score of 96 on the standard normal distribution is a z-score of 3. Okay, so if I go to the left, okay, what does a mark of 48% mean for this test? Well, how far are you away from the standard deviation? Okay, well, once again, you're one thing away from the standard deviation. There's one standard deviation from 60 to 48, but it's to the left. So you're going to get an answer, a z-score of -1. So what goes with 48 is a z-score of -1, where 36 is 2 to the left. Okay, so a z-score means how many standard deviations, okay, away something is from the mean. And we're going to always have to calculate a z-score first in order to find area. So your first step, okay, number 1, is always going to be find a z-score. Okay, well, actually your first step always, sorry, is draw a diagram. Okay, you can't see that. Okay, your first step is draw a diagram, fill everything in on the diagram, and then you're going to find a z-score. Raisa? Raisa? Will you keep an eye on the time? Just nag me when it gets to 11:50.
Yes, I will.
Okay. Raisa, Rosina, or Daniela, can I carry on waffling, or do you have any questions?
I've got a question, sir.
Okay, yes,
On the
Daniela.
Z values on the normal curve, the original curve with the 0, 1.
So what I'm going to show you an example now. What I do is I draw one curve, right? So if I was doing this diagram over here at the top, I would fill in my x-scores, whatever x-scores you asked to find, right? I'd fill in my mean, so I'd fill in that. And then let's say I had, this case, they asked me for an x, they told me, what's the probability of someone getting between 60 and 80, right? Okay. So what I would do then is underneath, I would write the z-scores that go with that x-score. Okay. I'm just going to show you quickly where we use the z-scores. Okay, why we need z-scores, and then I'll come back to some more questions. Okay. So we figured out for this particular sample, okay, those are the marks that go with each thing. Right. Now, what we discussed earlier, I want you guys now to have this table. You can either use your textbook or you can use your information sheet that I sent you the other day. On your information sheet, there's this table over here. Okay, so if you haven't got that available, get that available now. And what this is, okay, and there's a whole explanation at the top here, and I'll try to explain what this means. Okay, so this is your standard normal distribution table. These things over here on the side, and so on the side, guys, if you want to highlight it, those things are your Z scores. Okay, all these numbers on the side, in the blocks on the side. What these things are here, inside the main blocks, is this is your area under the curve. Okay, under your normal curve. So these things are your areas. Okay, for what? For your standard normal distribution. So in other words, okay, what this is saying to you is this is a table of areas under the normal curve. Okay, so these things in yellow, within this yellow square, those are areas. Sorry. Okay, those things in here, sorry, in this region over here, within that block, are areas under this, under a curve, under a normal curve. For what? Not for your X scores, okay, for your Z scores. In other words, for a standard normal distribution table, which has a mean of 0 and a Z score of 1 means 1 standard deviation from the mean. A Z score of 2 means 2 standard deviations from the mean. Okay, so we need a Z score in order to calculate area under the curve. And why do we want to know area under the curve? Because remember, in a normal distribution, what is area under a curve? It's probability, okay, of something occurring in that region. So if I wanted to, what's the probability of somebody getting a mark between 60% and 80%? Okay, I need to know the area under the curve because that is the probability. Okay, so you're going to always have to first get a Z score. Why do we want a Z score? We want a Z score so I can use this table to find area. Why do I want to find area? Because area is the probability of something occurring in a region. Okay, remember we can't talk about the probability at one specific score because it's continuous data, so that's theoretically equal to 0. Okay, now let's just have a look back here. And we discussed, can you remember, Daniela, what was the probability of something, and we did it just now, of something occurring within 1 standard deviation of the mean?
68%.
Good. Okay. So we figured out that this area over here, the probability of somebody getting a mark between 48 and 72 should be 68%, right? Remember, a mark of 48 is 1 standard deviation to the left, a Z score of -1. These are Z scores, eh? Okay. And a mark of 72 is 1 standard deviation to the right. Okay. So say you didn't know. Say I hadn't told you, or that they hadn't told you, that this area was equal to 68%. How would you use your table to figure out that this is 68? Okay, well, what you're going to do is this. You'd work out the Z score for 72. Okay, and the Z score for 72 is 1. So now you're going to go to your table. Okay, and what your table gives you, guys, it says here, H of Z, when they're talking about H of Z, that's your area under the curve. Okay, so this is, you don't have to know this formula, but what H of Z is an area. What area is it? It's the area between 0 and Z. Okay, so it's this area over here. This is what this table is giving you. Okay, it does not work with negative Z scores. I'll show you what happens with negative Z scores now. Okay, but what this table does is that H of Z is an area. So this is telling you that this table is giving you the area. H of Z is the area between 0 and whatever the Z score. So H of 1, so this area over here, in yellow here, this is, we could refer to this as being H of 1. What does that mean? It means this is the area, okay, between Z is equal to 0 and Z is equal to 1. Okay, in other words, it's the probability. Okay, and we said this, we predicted that this whole area should be what? We said it should be 68%, in other words, 0,68, right? So Daniela, if the whole area is 0,68, what do I expect just this half to be over here? That pink bit. if that whole area in yellow is 0,68, what do I expect the pink bit?
0.34.
Good. I expect that to be 0,34, right? But now I want you all to go to your Z table. Okay. And we're trying to figure out, okay, I'm looking at a diagram where I want to know between 0 and 1. Okay, between 0 and 1, what is that area? This is what this table is going to give us. So I go to 1, 0. Here's my Z scores, right? I want this over here. The top thing, guys, is your second decimal place. So for instance, if I wanted 1,05, a Z, so if I had a Z score of 1,05, what would you do? You'd go to 1,0, but now you'd want 1,05. So 1,05, where do those two columns meet? That area would be 0,3531. Does that make sense? Okay. This is your second decimal place. So if you had a Z score of 1,05, then what would your area under the curve be up to 1,05? 1,05? Then that area would be 0,351. It would be this Z score over here. I mean, that would be your area, 0,351. Okay, however, what we're looking at here is, Daniela said this area we expect to be 0,34. What's the Z score here? It's 1,00, right? So if I go to 1,00, I'm looking at this area over here. Okay, so that is your area under, what have you worked out there? That's your area under your curve. Okay, between, if we go back over here, we've worked out that between, for a Z score of 1, this area is 0,34. Okay, that area in pink. Okay, to be more precise, this area over here is 0,3413. Okay, so that area, let me just scribble this somewhere. So what you've worked out is that if you have a normal distribution, so your process that you're going to do is this. Let's say we're taking the sum from the beginning. If we had a mean of 60, okay, so you'd write down your mean always. Okay, mu is equal to 60. This is going to be the process we're going to use, right? And then you wanted to know what's the probability of somebody getting between 60 and 72%. Say that was the question. Okay. And they told us your standard deviation is 1. Okay. What would you do? Well, you'd first go work out your Z score. And you'd say Z is equal to the X score. Those are your X scores. Minus mu over standard deviation. Right? So in that case, it would be 72%. I'm just going to say 72 minus 60 over 12, which gives you 1. So then you'd say, wow, now I know underneath this is what I do. I don't do two diagrams like the textbook does. I say I've got my X score of 60 and 72. For the mean, what's your Z score always? It's 0, right? 60 minus 60. This has got a Z score of 1. Okay. Then what do? You say, okay, I want to find this area over here. There's no complications there. This is what the table gives us. This area over here that I've shaded in would be H of 1. In other words, the area between 0 and a Z score of 1. So now what would you do? Okay, just to remind you. Now you'd go to your table and say, okay, where's the Z score of 1,00? A Z score of 1,00 is here. And it's 0,3413. So what has the table told you? It's told you that this area over here is 0,3413, right? Okay, so that area over there is 0,3413. So to answer the question, what is the probability, okay, of somebody getting a mark, an X score between 60 and 72? Well, that's the same question as somebody saying what's the probability of a Z score between 0 and 1. And from the table, you can see that's 0,3413. In other words, we'd expect 34,13% of students, which is close to 68. That's where that number 68 comes from. Okay, so that's where that 68% comes from. If I said to you now, okay, we've got 5 minutes left, what's the probability that somebody gets between, if I go 12 to the left, between 48 and 72? Well, now I'm including this whole area. Okay, so what would this area to the left be? Well, let's just say we hadn't done this one over here. Well, what you'd do is you'd say, okay, 48%. For 48%, what's the Z score? And you're going to use Z is equal to X minus mu over sigma. And the X score is 48. Okay, and mu is 60. and sigma is 12, so you get -1. So you'd say self, this over here is -1. You've got a z-score of -1. Now what's the problem? There's no negative z-scores. But why doesn't it matter? It doesn't matter because the area between 0 and -1, in other words, the probability of between 0 and -1 on a normal distribution will always be the same as the probability between 0 and 1. Okay, so I don't have to, I can't look up a z-score of -1, so you just look up a z-score of 1, which we know is going to be 0.3413. So this area here is also 0.3413. So if I said to you, what's the probability that somebody gets between 48% and, probability that X is greater than 48 and less than 72, okay, well, that's the probability of your z-score lying between -1 and 1. And we know that that's going to be 0.3413 times by 2, which is, I think, 0.6826. So actually, the exact answer for what falls within 1 standard deviation, okay, is 68.26. So that, guys, is your main process, okay, that we're always going to do. Okay, you're going to be given some information. You're going to be given a sample set. You're going to be told this sample is normally distributed. Okay, what's the probability of something happening? So it could be, what's the probability of getting a mark greater than 72%? Just quickly, if I said to you, what's the probability of somebody getting a mark greater than 72% in this case? Well, what's the area we're looking at? The area I'm looking at is this green area over here. If I said to you, what's the probability that somebody gets a mark greater than 72%, right? It's that green area over here. So how would you figure out that green area? Well, you couldn't figure it out directly. You'd have to go figure out this area over here in yellow first, which is what we've done. And that area is 0.3413. Guys, the whole area under the curve is 1. So if the whole area under the whole curve is 1, then to the right of the mean, that area is equal to 0.5. So this whole area to the right of the mean is 0.5. So the green bit over here, how would you work it out? You'd say, well, the green bit, this whole area is 0.5 to the right of the mean. So the green bit must be 0.5 minus 0, what was that area over there? 0.3413, which is whatever it is, 0.5 minus 0.3413, and you get an answer of 0.1587. So in other words, in this case, there's a 15.87% chance that somebody got a mark bigger than 72%, or you could say we'd expect 15.87% of students to get a mark for this test bigger than 72%. Okay, right, it's time for you guys to go, and I know we overdo things. Just go back and do those pages again, guys, and I want you to try, just for homework. Okay, you know what? Don't worry about that. We'll go over example 2 in the next lesson. We didn't do as much as we wanted to, but that's fine. Okay, I want you just to go back and make sure you've read and filled in your notes. Okay, as I said, don't worry about this whole bit over here. But from page 158 through to page 162 up to the table. So up to page 166. Just please work through those notes again. Fill in the worksheet. I know it sounds a bit lame just copying out the textbook, but it's just forcing you to engage with that work, and you are going to submit that through to me as a scan once we finish the chapter. The three of you, did any of this help?
Yes, it did, sir.
Okay. Are you okay with me not doing videos for this section? I just think videos for this section are going to be difficult in terms of working on the whiteboard and trying to see what's going on. Should we do just if you guys need to go, the rest of you can go. Can the three of you just give me 2 minutes? Guys, should I
kind of like how this is working. I think it's working fine.
Okay, but do you think, should I make you read through the stuff first? Are you happy with the first lesson of a double being for you guys to try work through stuff a bit yourself? Or do you want me to go straight into that?
No.
Yeah. Not really.
Daniela, what do you think?
Can you not record what you're doing right now?
It is being recorded. I'm going to put it up on Teams.
Yeah, like, because you're visualizing the thing, right? And then can't you just record what you're explaining and then upload that as a video?
It's pre-recorded. What happens, the problem with pre-recording is I could do that. I could try to do that. Would you rather I did that?
Because then, like, we can all go at our own pace and, like, fast forward
And
or,
also
like,
pause it.
go back
Yeah.
if we need. Yeah.
Okay, so okay, let's try to do that. What I'll do is I'll have an imaginary lesson with an imaginary friend, and I'll record that, and then I'll put it up on Teams. It has to go into Teams. I can't put it as a YouTube video, I don't think. Okay. And then when you're working through your examples, so the first part of the lesson would be working through your examples from that. Then what I'll do in the second part of the lesson live for those who want to join is I will go through, I'll do some, for those who want, I'll do some exercises from the textbook live for those, only for those who want to join. Should we try that?
Yes, please.
I think that
Yes,
works.
yes,
I
that's
prefer the
fine,
live
sir.
sessions.
Okay. Daniela, should I try that?
I don't mind that.
Okay. Rosina,
Yes.
any other suggestions?
No.
Raisa?
That's fine, sir. Thank you.
Okay, then you can go through. I know what it's like to try stick to times is really difficult with this online stuff. So I'd rather have some flexibility in joining or not. Okay, guys. This will go up onto Teams. Just go back and try those pages again. And otherwise, yeah, good luck with everything.
Thanks, sir.
Bye, sir.
Thank you.
Okay.
Bye, sir.
Bye.
Bye,
Bye.
sir.